Recall the relationship between a function and its inverse. Essentially, for any function that is invertible, you can swap your points x and y. So if we're looking at a function f of x on the screen and we pick out a point like 4, 2, that means we traveled horizontally 4 units and vertically 2 units. For the inverse, we would swap those directions. So instead, we would travel horizontally 2 and then vertically 4. We can do this for every point on our original function, and it would generate every point on the inverse function. We also know that for inverse functions, that when we create the composition, the result is always x. So f with its inverse plugged into it will give you the original input, x. Or f inverse with its original function plugged into it will give you the original variable x. So these are properties of inverse functions that we've seen before. But now we're going to build on this and talk about how rate of change is seen between the two functions. The rate at which our original function changes happens to be the reciprocal of the rate that the inverse changes, and graphically we can kind of justify why. We have a tangent line to f drawn at the point 4, 2, and we have a tangent line to f inverse drawn at the point 2, 4. These two lines, they're not parallel, they're not perpendicular, but they do have reciprocal slopes. Remember, we swapped our x's and y. So on the original function, our slope of that tangent line goes up 1 over 3. And on the inverse function, the slope of our tangent line goes up 3 over 1. So we've flipped that ratio over. Our rate of change has been reciprocated. So if we ever needed to calculate the rate of change for an inverse function, we can actually use the rate of change from the original function. Why is that the case? Well, let's start with that property we remembered from our pre-calculus class. The composition of a function with its inverse will always be equal to the input variable. In this case, it's x. If we take the derivative of the entire equation and we apply the chain rule for the composition of f with its inverse, we get a new equation that says the derivative of f with the inverse function plugged in times the derivative of the inverse function is equal to 1. If we solve that equation for the derivative of the inverse function, essentially we just need to derive by f prime of f inverse. We get this formula that says the rate of change of the inverse function f is equal to 1 over the rate of change of the original function with the inverse plugged in. Let's see how to use this in an example. We want to verify that this theorem does work using the function g of x equals x plus 2, all divided by x. So we're going to use the inverse function theorem, and we're going to differentiate directly so that we can see that we'll get the same results no matter which way we do it. The inverse function theorem says g prime will be equal to 1 over the inverse. I'm going to use f to talk about the inverse instead of g inverse, just to simplify notation. So f is going to be the inverse of the function g. That way I can say 1 over f prime with g plugged in. It'll be a little easier to discuss. So first we have to find that inverse function. We have to find the function f. Looking at g of x, we're going to replace the g of x with an output variable y. Then we swap the x's and y's. So we start with y equals x plus 2, all divided by x. When we make the swap, it becomes x equals y plus 2, all divided by y. Solving that equation, the x equals equation for y, we will be able to find the inverse function. So going through our process, we just need to use the basic reverse PEMDAS to be able to find the equation y equals 2 divided by x minus 1. So we found our inverse function f. Now we're ready to use it in this inverse function theorem. To find the derivative, I'm going to apply my derivative rules. I'm going to rewrite my function as a negative exponent. That way I can just use the chain rule instead of a quotient rule. So we're able to find the derivative of f, which is the inverse to the function g. We need to use that in our inverse function theorem. So let's build the denominator for that theorem. Let's find f prime with g plugged in. We know f prime is -2 divided by x minus 1 quantity squared, but if we plug g in, it becomes -2 divided by g minus 1 quantity squared. And since we know what g is, x plus 2 all divided by x, we can plug that in for g, and then we can clean that up a little bit. So I'm going to spare you the arithmetic algebra right there, but we just combined our terms in the denominator by finding a common denominator and simplifying. And now we can simplify a step further, applying that exponent to the entire denominator. And lastly, we're dividing by a fraction, so we'll take the fraction in the denominator, flip it, and multiply it to our numerator to find that f prime with g plugged in is -x² divided by 2. That will be in the denominator of our inverse function theorem. So 1 over that is g prime. Again, we're dividing by a fraction, so we'll flip that denominator, multiply. We're able to see that g prime should be equal to -2 divided by x². That is all using the inverse function theorem. And you might be thinking, that's a lot of work written on the screen. And you're right, this is not a great application for this theorem, but it is one that we can verify by using traditional derivative rules. So let's now calculate g prime using the quotient rule. We would calculate the derivative of the top, multiply it to the bottom function, minus the derivative of the bottom function multiplied to the top function, and then that whole expression is divided by the bottom function squared. So that's our quotient rule for the function g of x. Evaluating our derivatives, we get x minus x plus 2 divided by x². And what do you know? When we simplify, we get the exact same answer as when we use the inverse function theorem. All of this is to say, the theorem works. We were able to calculate the derivative with the theorem and calculate the derivative without the theorem, and we got the same results, which is exactly what we want. Now let's take a look at an example where it matters. In this case, we want to be able to find the derivative of an inverse trig function. We don't have any rules for that at this moment in time, so if we didn't have this inverse function theorem, we couldn't find the derivative of this g of x. So let's go ahead and use it now that we have confidence that it does work. Recall that our theorem says that the derivative of g would be equal to 1 over the derivative of its inverse, evaluated at g. So we're going to start again by finding the inverse to our function. So we have g of x is sine inverse. We need to find the inverse to that. So I will set my function equal to y, swap my x and y's, and then using the definition of sine and sine inverse, I can just rewrite that expression to say sine x is equal to y. So that would be the inverse function, but recall that a sine function is not totally invertible. When you invert a sine function, you have to truncate the domain. So this inverse function, f, is only valid for x values within the range -π/2 up to π/2. So we have our inverse function f. It's the inverse to the g function that we're working with. We'll take the derivative of that, find it to be cosine, then we can find the denominator for our theorem formula. We have f prime with g plugged in, so that would be cosine with g plugged in, and since we know g is sine inverse, we have cosine of sine inverse of x. Now, we're going to need to build on some of our trig foundations here to figure out what that expression really means. Recall that cosine takes in an angle. So sine inverse of x has to be an angle, and we've said that that angle has to be between -π/2 and π/2 because of the inverse situation. So let's consider this as cosine of some angle theta. And let's draw a triangle to figure out what that would look like. So we'll come back to this after we draw our triangle. Sine is a ratio of sides of a right triangle opposite over hypotenuse. Cosine is the ratio of adjacent over hypotenuse. We want to use a triangle like the one on the screen, just a generic right triangle, to figure out what cosine of sine inverse of x would have to be. So we first separate the sine inverse part and the cosine of the angle part. That way we can deal with this in stages. Sine inverse of x is going to be the theta in our triangle. And we can use the properties of sine to rewrite that as sine theta of x. We talked about this on the previous slide. But now we can say sine theta is a ratio of opposite over hypotenuse from a right triangle. To simplify things, we're going to make the hypotenuse of our triangle equal to 1. That way we can eliminate one of the 3 unknown sides in the triangle. We know that this will be true for similar triangles. That's the beauty of using a ratio for sine theta rather than just a fixed number. So we're going to replace hypotenuse in that expression with 1, meaning the opposite side has to be equal to x. And we'll label that on our triangle. So now we have 2 of the sides of our triangle determined. One of them is the hypotenuse, it's equal to 1. The other is the side opposite of our angle theta. We're calling that x. Now let's move over to cosine theta. We know cosine theta is the ratio adjacent over hypotenuse, and we've fixed the hypotenuse to be equal to 1. So we can see that actually cosine theta is equal to the adjacent side of this triangle. Now we're going to use the Pythagorean theorem to solve for that third missing side, the adjacent side, and that will tell us what cosine theta is. That's what we're looking for after all. Pythagorean theorem says the sum of the squares of the legs of a right triangle is equal to the hypotenuse squared. So we'll have the adjacent leg squared plus the opposite leg squared, and that'll be equal to the hypotenuse squared. And since we know the opposite side is being called x and the hypotenuse is being called 1, we have adjacent squared plus x squared equals 1 squared. We want to solve that equation for the adjacent side. So let's subtract x squared from both sides. And then let's square root both sides so that we can isolate the adjacent term in that equation. Now we can see that the adjacent side of this triangle is 1 minus x squared, all inside of a square root. That is what cosine theta is equal to. So remember, cosine of sine inverse of x is what we are calling cosine theta. Coming back to the problem we were working on, we can now say that f prime evaluated at g is 1 minus x squared, all in a square root. So we used our right triangle to determine that that's what it would have to look like. Now we're ready to complete the inverse function theorem. We've simply calculated the denominator. Coming back to our theorem, we need to replace the denominator with what we found it to be. And then we can conclude the derivative of sine inverse is 1 over the square root of 1 minus x squared. And we were able to determine that by using the inverse function theorem.